Okay, have you seen the the screen that I share here? Okay, perfect, yes. All right, so these are the material. We shall do some checklist and see some more examples, or let's do some problems or any of your questions. Okay, so we'll checklist, especially things that are critical. That's pretty much quite often it appears on the test, the exam. Okay, so our test's going to be from the beginning, the very beginning, until 3.6. So up to here. So we stop here. Okay, so let's briefly, it looks like quite a lot, but actually, there are only a couple of things actually. All right. So let's see the from the beginning. I think from chapter 0, what you need to uh, really review is this one: inequalities, absolute value. Okay, so that's one. Recall how to solve absolute value inequalities with absolute values. Okay, and recall how we interpret that as distance. Graph evocations, we always use this one as a basic tools. So you need to graph. You know how the basic transformation of a graph translate up, down, left, right, diagonal. So this all together. Let me just graph and functions. Okay. And this one here is compositions. Compositions and decompositions. Okay. And trig functions. Basically, those what you need to review from chapter 0. Okay. But since we use this almost all the time, so the material you see that's only this one: inequalities, absolute value, graph, trig functions. And then chapter 1, let's see, what you need to find is to review is this one. That's the error estimate, epsilon delta, I think. Okay. And also that's the, say, one of the most difficult part of this semester calculus course. Limit theorems, you need to know how to compute limits, use the properties of limit, involving trig limits. Okay, so all the things together. Okay, and continuity of functions. Okay. And derivative, now derivative is quite a lot actually. Two problems is one theme is just the description of derivative as a slope of a tangent line and instantaneous speed. Here you can, this is definition of limit. So you need to able to be able to recognize limit using, sorry, derivative using limit in quite a few ways. Rule for finding derivative, you always use this one, including chain rule. So this all together. So higher order derivative. Okay, we mostly use just only second derivative. We haven't used quite much third or even higher derivatives. Implicit differentiation related traits are actually just one thing. Differential approximations. That's what we had last week. Okay. And this one, you can lump this one into graphing. You know how to do graphing, then uh, you know how to do this 3-1 till 3-4, 3-5. And mean value is, I would say, something that we will use often later on, but not much really for this midterm test, except that a couple of things we in graph sketching actually needs mean value theorems, but that's under the surface. You can say that, so you won't see uh, questions directly ask you about the mean value theorem. So that's basically the material for the midterm exam. Okay, any questions?
Sir, can I ask about the asymptote?
Sure.
I don't kind of get it about the materials.
All right, so let's put the asymptotes all together. So the horizontal, vertical, and then also the slant asymptotes. Okay. Okay. So what we are actually computing here is the uh, rational functions mostly. So f in the form of this. So polynomial over polynomial. Okay. So for example, that's all right. So it's about the uh, rational functions. And we won't uh, go over the asymptotes in context outside the rational functions. So always rational functions. Okay. Okay. So how to recognize asymptotes easily? All right. So let's see how to recognize this. First of all is the what you call the vertical asymptotes. Vertical asymptotes. You see, this is vertical asymptotes. If you can say just, or you can say also one-sided limit. You can have plus infinity or minus infinity. Okay, so what you have situation is this one. That's asymptotes. Okay, so this is the definitions, but you can find easily by looking at the root of the numerator of q. So the question is how to find a. So usually what you have here is uh, the roots of the q. Okay, so remember this is x, this is qx. Okay, so whenever this is 0, but not root of p. Okay. Okay, for example, uh, let's say we factor in factored form. Uh, mm, okay, all right. You see that the uh, our candidate for the asymptotes is this three numbers here. A is from here, this is 1, this is 3, and from here, this is 1/2. Now the question is, okay, if yes, then you can simplify, you can cancel some power. But if not, then that's all the asymptotes. You see that just plug in the number here. If you plug in 1, 1 minus 1, okay, 7, okay, on 0. Plug in 3, 3, you have 27 minus 1, 26 plus 7, non-zero. If you plug in 1/2, 1/2, oh, for sure, that's non-zero. So, okay, so this is our vertical asymptotes. X minus 1, x minus 3, x minus 1. Okay, and you can check easily that the limit of a in this case. Okay, but to find the vertical asymptotes, that's easy. Is it okay?
Okay, sir.
Okay, now, so whenever you don't have the denominator is never 0, then you won't have uh, vertical asymptotes. do one more example. For example, this one here. Okay. You see this one here? So our guess is asymptote is for A equals 1, 2, 3, right? Because that's the zero of Q, P over Q. Okay, so that's our guess. But let's see here. Let's check here. The thing with one also appears here. One also zeros of the P. Okay? So in fact, we can simplify this first. In fact, for this one, root for P of x is not zero. Okay, so the vertical asymptotes is only it's A to the asymptotes. Okay, so you can check that. All right, so now let's see the horizontal asymptotes. Okay, so this line y equals say b is horizontal asymptotes. If going far to the left or going far to the right gives you the number b here. If okay, say going far to the left or far to the right. Uh, so that's easy because you don't have to guess. In horizontal asymptote, sorry, vertical asymptote, you make a guess first. Your guess is based on the zeros of the Q denominator. Uh, and horizontal asymptote, you don't have to make a guess. You just compute the limit. Okay. If you find the limit, then it is the horizontal asymptote. Okay. If not, if there's no limit, then you don't have asymptotes. So example. Also, the context is rational functions. Of course, we know that oh, let's use these numbers. Okay, that's one example. Okay. You don't have to worry about the zeros of either P or Q. Just all right. Since we know that how to compute this limit, that is to divide by x to the fifth, right? So the highest power. So you get this one, this limit. So this one over x, 7 over x cube minus, which all goes to 0. This is 1. So this goes to 0. This goes to 0. This goes to 0. So what you left is this one. But here they have 0. Okay, so the conclusion is that this limit y equals 0. So that means x-axis is horizontal asymptote. Okay. Or you may have something like this. Okay. So in this case, the limit is that's easy because this just you divide by square, right? So in the end, you have just 1. In this case, that is the horizontal asymptote. All right. And another example. For example, all right, so just take this one. There. Okay. Um, right, so let's divide this by you can divide by x squared or divide by x cubed. Just x cubed. Divide by x cubed. And divide by x cubed, this becomes 1. This goes to 0, this goes to 0, goes to everything goes to 0 in the denominator. So you get the end you have there. Right? So in this case, no horizontal asymptotes. Asymptotes. Okay. So you see, you start to observe that the this will go to infinity. Okay, this is getting large. If the power or the degree of the polynomial and the numerator is larger than the denominators. Okay, so this is power 3, this is power 2. Okay, of course, you have this. Okay. So the conclusion is that horizontal exists, horizontal exists um, if you see the power degree of p. Okay, so this is f p over q. Okay, so both p and q are polynomial. The degree is at most the same. EQ of q. Okay. Okay. So, and now you expect something that looks like this one. If the, okay, so if P over Q is something that looks like you can divide, but you get ax plus b. So that looks like this. But some residue. Say this is residual from these divisions, meaning that the degree of R is less than degree of Q. So you cannot divide further. Okay. If you get this one, then this is something that we call because if you have the degree of R is smaller than the degree of Q. Okay. So if we take this limit, this goes to zero as okay. So this will disappear eventually, and you live with this linear thing. This is what we call the slanted asymptotes. Y equal Ix plus B. So and this happens, of course, this won't happen if say P is power 10, Q is power 6. So if you divide them up, you still have power 4. Okay, so this won't happen. Okay, so it only occurs if degree of P, okay, so it is one more than the degree of Q. Okay, all right, so example equals there. Okay, of course, if you divide this up, let's see, let's do some long division, not really long actually. If you divide this up, then you get square, and you let's see how to do this one. This is x squared minus 3x. You subtract, so you get become 3x minus minus. Okay. Divide by 3. Okay, you still get 3. 3x. This is 3. Okay, so x disappear. What you have is 1 minus minus, that is 10. Okay, so it turns out that we can write this as a 3 plus what's left? Left is this. Yeah. Okay, so then this one goes to 0 as x goes to infinity. This is long, but x is large. So what you left is this one. Okay, so our conclusion is that y equals x plus 3 slant asymptote. Okay, questions? All right, so you know how to find asymptotes now just by looking at the form. Vertical asymptotes, that's the zeros of the cube. Okay, and horizontal asymptotes, then the degree of the numerator is at most the same as the degree of denominator. Okay. If not, then forget about the horizontal asymptotes. Slant asymptotes only occurs when P is 1 larger than Q. Okay, that's a slant asymptotes. All right, so let's summarize what we have about the asymptotes. Questions?
Can you scroll up the screen a bit, sir?
Which one?
Already, sir, already. Okay.
Right? Okay.
Sudah, enough. Thank you, sir.
All right. Okay, other questions?
Can we talk about the squeeze theorem?
Squeeze.
I'm a bit
All right.
confused.
Okay. Squeeze theorem. All right. Squeeze tells you that if you have, say, three functions, you have a G is squeezed between F and H. Okay. Now it squeeze only in a certain part of the domain, not necessarily in the whole domain. Some intervals. Intervals containing that's the point of our interest actually. That's A. Okay. Now, if that happens, then also if now the squeezing thing is this one here. If you take the limit of the left and right, then that's equal. So we can conclude that, well, the G must also be equal. Say this is L, they coincide, then it's limit. Now, okay, so the meaning of this is that here we can compute limit without actually directly computing. So this is indirectly, but where to compute is the lower and the upper bound. Okay, so the squeezing thing. Instead, compute the limit of the upper and lower, in which the limit, the upper limit equals the, say, lower limit. Okay, so you don't have to deal with G directly, with the limit of the function directly, but it will be implied by limit of the lower and the upper. Okay, so that's the thing about squeeze principle. Okay, so let's do some example. Oh, remember that the uh, thing that I asked you to compute in the homework one about the what you call it, rounding numbers and taking limit. Okay, so that's one example of the squeeze principle. Okay, so let's do this one. Let's find. Okay, so you don't have any other tools than working with this because um, let's say all right, do you remember how to compute this one? Round down, rounding x. So the natural, not natural, but a integer less or equal to x. Integer actually, sorry, not only integer, largest integer okay. So how will you compute this one? Okay, the thing here is that what you say if x is less than, sorry, it's bigger than, less than n plus 1. So this is squeezed, not really squeezed, but between two integers, n and n plus 1, and the next one is the plus 1. So we say the integers is n. Okay. X is always between two integers. Two, I would say not two integers, consecutive. What can we say is that this is x and it's n plus 1. And because you do rounding number, so this equals to x on x. Okay, so this is also, if you, here is x plus 1. If you add 1, then here you have x plus 1. Okay, so you have some squeezing thing here. Okay, so for this squeezing thing is that, let's compute this one. Okay, there we go. All right, so to find some upper bound, okay, so either you increase, not either, you can do both. You increase the numerator, you decrease the denominator. Okay, so remember this. To make it bigger, increase A, decrease B. All right. If you find something smaller, then decrease the top and increase the bottom. Okay. All right. So in this case, let's just fix the x. Okay. And let's make this rounding bigger. So here we have this one. So it is, it will be there. So it is squeezed by okay, and it's, oh sorry, to the right. That is x. You can use also this one, but it's not necessary. Just use this. And something smaller, so the x minus 1. Okay. Oh, that occurs for every x. Okay. Further, if you compute this limit, because they are same power, so just the ratio of the coefficient. That's 1. And this limit, the upper. Okay, so you have this squeezing thing. So limit by squeeze. Okay, so the key here is to find the upper and the lower and the upper limit. Example 2. This is one of the not to say most often, but often appears in the exam is pupils limit. Say this one, or let's make it more extreme. It doesn't matter. X 50. Okay. So how we deal with this one? So we know this one, x goes to 0, right? So this is large. So 1 over x. So if this is large, then you can say this is a what they call the extreme oscillations. So you don't have limit. But what so that's one. Okay, but how if we multiply this by x squared? Okay, so let's do some squeezing thing. Okay, so you know that cosine is always between -1 and 1. So this holds for any x non-zero. Okay, let x non-zero, then simplify. Okay, so if you multiply this out by x squared, okay, you multiply by something non-negative, so it won't change the inequality. All right, so if you multiply negative, so the thing in the middle should be the one that asked in the problem. Okay. And then you know that this limit is equals. Okay. So by squeeze principle, Squeeze theorem, this limit. Okay. See that we didn't compute this limit directly. So we don't deal with x squared cosine 1 over x to the fifth directly. But instead, we're looking at the lower and upper bound. Okay, after this one.
Yes, sir, I understand.
So pictorial here that looks like this one here. Square is minus x squared is this one. So the and x squared, right? So where is the cosine? Cosine thing is this, right? Okay, so what we find the upper and lower is the one that squeezing thing from the top and from the bottom. You see that here, the squeezing actually coincide at this point. And for just do same thing. Okay, so this pictorially what the squeeze theorem about. Okay. All right, so let's take a just maybe 3 minutes break. So I won't make the not to make the video too long.